All right, it might.
You're not checking the homework, are you? They did do it all.
Good.
Really
I wouldn't learn much from this. I mean, you could just type in your calculator. Sometimes I just get depressed when I do.
They did it.
That's good. No, you guys, I'm sure, would be fun.
Us, we would be, but your other people,
Some of those.
they would not be as trustable. I mean, you have stinkers in there like saying, actually I asked about that.
Yeah. I was facing Justin Tucker. He beat me by 1 point in the semifinal. I was up by 22.
Well,
And he beat me.
All right. Yes, Alex, try to focus today. I know it's going to be hard for you with you.
it's like zero.
Closer. It's good. You're taking it well. You're taking it better than I would.
Alex, it's like looking in a mirror.
All right. Let's begin.
That sounds long.
Well, 16. Yeah. We'll actually walk through probably each one and check them very quickly here. But there are a number of issues. The first thing I think I would like to go through with you, even before we go through and check and talk about these, because there's so many different, when you get into limit problems, so many different things that can happen. I mean, on today's homework, you're going to have some, or the homework for tomorrow, you're going to have some graph ones thrown in there, some other things. And so we really have to understand the overall concept. I mean, it's not enough to just, oh, I do this, then I do this, and then all of a sudden, then another one comes up with something a little different. You've got to really think about it. So, I mean, let's approach it this way. What are some situations? What are the different things that can happen when you should be saying that the limit does not exist? What would be one scenario? And even going back to chapter 2, when the limits we did there, in the video with the cars and stuff. Cody? No. 0 over, now let's talk about that. What would happen if you get 0 over 0? You keep going. Now, could you then get something where the limit does not exist? Yes. But just getting 0 over 0, we do not know that the limit is not going to exist. A number over 0. So one situation is you get like 4 over 0 or something like that. Now, we have talked about how that means a vertical asymptote, right? That's how we talked about it earlier. All right, now an example, let's do an example of that. An example of that would be something like limit as x approaches 2, x plus 2 over x minus 2. That would be a situation where we would get 4 over 0, right? You plug in a 2, on top you get 4, on the bottom you get 0. The limit does not exist. Now, vertical asymptote is a graphical thought, but if I was confronted with this problem in a no calculator situation, I probably wouldn't be thinking vertical asymptote, right? I wouldn't be thinking of the graph, probably. But we would say does not exist. So what would you do on this problem? You would go to the right and the left. Anytime the limit does not exist, you must follow that up with some justification. You must follow up your does not exist with some justification. The usual justification is the left and the right limits. Because if a limit does not exist, the cars don't meet. So one way of saying why the cars don't meet, or it doesn't approach a number, that's probably a better way to say it. You should get away from this kind of cars don't meet thing, and we should talk about the limit needs to approach a number. The output needs to approach a number. That's where the cars meet. Well, this one doesn't. Now, where are the cars going? If you have a vertical asymptote situation, where are the cars going? Positive or negative infinity. Now, they might both be going to positive infinity. might both be going to negative, or one might be going one way and one the other. That's what you're trying to find out. And again, when you get 4 over 0, what you're really getting is 4 over something really small. You're getting 4 over something really small is what you're really getting. Not 4 over 0, but 4 over something small. So the question is it small negative or is it small positive? Right? That's the question. Well, how do you get that? Well, one way we said is you write down, okay, 2 from the left and 2 from the right. So this would be like 1.99, right? Well, that'd be a small negative. So this would be 4. Now, it'd be a little less than 4. 2 from the left would be like 1.999 plus 2, so it'd be 3.999. But basically that's 4. That part doesn't matter. And then you're going to get a really small negative. Well, what's 4 divided by a small negative? It's really still 4 over 0, right? But which side is 0 is it on? Because it's approaching 0. Well, that's negative infinity, right? And so we get that. And then 2 from the right, 2.001 minus 2 is a really small positive. And so we get that. And so that's positive infinity. So now so this is your justification. These two things right here is your justification for why this does not exist. Okay? Now you're going to have some in your homework where what if instead of this right here, well, I'll just let you think about it. But if I had a graph, let's just put it this way. If I had a graph and this was 2 right here, right? As x approaches 2, what is that limit? For this graph right here, as x approaches 2, what's the limit? 0. From the left, it's 0, but from the left, what do you got? What kind of y values do you have when you're just barely left of 2? Small negative, right? And just to the right of 2, small positive. So you see how this down here, the small negative, small positive, could also be seen from a graph, right, of something, right? Matter of fact, if we graphed x minus 2, this is a graph we would have. It'd be a line, right? X minus 2. Just to the left of 2, you got small negative. Just to the right of 2, you've got small positive, right? So we could see those kinds of things graphically. Now, another situation where limit does not exist was this kind of a situation, right, where we had breaks. Right? We're probably not going to run into that so much today on today's homework, but or on this quiz, because we're dealing more with the quiz. That would be like a piecewise function, right? Car on the left's coming here, car on the right's coming here. That is a does not exist situation too, right? But the one we're going to run into the most here is going to be this situation. All right? So you need some sort of justification. Now, what about, well, I'll tell you what, let's get into the homework here a little bit and we'll come back to this. All right. Oops. So what did you have for an answer on this one? This is the first one. This is number 9. 0. Right? You have 3 over a really big number. That's 0. Okay? No work to show, nothing to do. What about this one? Still have a really big number on the bottom, right? 5 over a really big number. Now, it's not as big as an x squared, right? X squared would be getting bigger faster than square root of x, but it's still a really big number. Okay, what about this one? Why? Somebody, Spencer? No, you either Logan? We talked about being able to just ignore these. But we do have to be careful. We can't always just cross those out, right? Why can we ignore the 3 then? Logan? Yeah. Since this is going to infinity, 2t is really big. And so the 3 is insignificantly small compared to the 2t. And the same thing with the 5 here. So that's why we can ignore. So that becomes 2t over negative 4t. The t's would cancel. It would reduce. And you get that. Okay? Anybody else with a thought on that one? Okay. What about this one? Now, we need to talk about that a little bit. You really, I'm going to go ahead and accept that if all you have on the quiz is that. But what else should really be there? Because a limit really means a number, right? It's as x approaches this, what is the output approaching? Now, this is kind of a special type of limit. When x approaches infinity, we don't really have x approaching a number. So in that sense, is it okay to say that the output's approaching infinity and just say infinity instead of does not exist? I think from a technical standpoint, limits, if they exist, equal a number. If they don't exist, an example would be infinity. Okay? Because the cars don't meet at infinity. It's going on forever. So so this would be a special situation. So let's go back to what we were talking about earlier, where I was talking about when do limits not exist. This was when we were talking about the limit as x approaches a number. We're going to get this kind of a thing. That's when limits don't exist. Thank you. But another situation that happens a lot is when x approaches infinity. So what was that one we just had? X squared plus 1 over x. Okay, the 1 is kind of insignificant. We get x squared over x, which would be just x. And so we would say this is infinity. It's really probably best to also have does not exist. But remember, my directions are going to say this. If the limit does not exist, justify why either using one-sided limits, etc. To me, this is your justification right here. Just having infinity. So I'm going to allow, and they did this in the back of the book, if on one of these where x approaches infinity situations, if you have just infinity, I'm okay with that. But on one like this, where it says, where we plug in, we get something over 0, I want it to say does not exist, and then you check the left and the right. We can't check the left and the right on infinity, right? As x approaches infinity, we can't go to the left and the right of infinity. Okay, we can't do that. So our justification of that it doesn't exist is, hey, it's not a number. Right? If a limit exists, it's a number output. Infinity is not a number. So I just kind of have mixed feelings about that, but it's kind of a technicality. All right, so either have both, or I will allow you to, if you just have infinity, I'm okay. Yeah.
So what about problems like number 9, 3 over x squared, where it's, and the limit is as x approaches infinity, because they don't really need it 0.
Right.
It's just an idea. So what that one does not exist.
Well, no, because it's a number. It's okay. You're right. Well, that's more a failing of the example of the cars meet. The cars can't meet anytime you're doing an x approaches infinity because you don't have two cars, right? I mean, we're not doing so. So the whole concept of where do the cars meet only applies to x approaches a number, right? If we're doing limit as x approaches 2, x approaches 0, x approaches 4, because then you got cars coming from both sides. When we're doing x approaches infinity or negative infinity, it's just one car. And what y value is it approaching? That's what we're saying. So this is 0 because as x goes way out there, that car is approaching 0. So, and it's a number, so that's why we just say it exists. Okay? So, analogies like that are great, and they help us with our understanding, but then they sometimes fall apart. They're simplistic, and we're using simplistic things for some kind of fairly technical, complex ideas, and so sometimes they don't. There's some gaps, and we got to make sure we fill those in. That's kind of the thing. All right, what about this one? 1/2. Again, as x gets really big, the 1 doesn't really matter, the 3 doesn't really matter. The x squareds cancel, you get 1. Okay, what about this? Back up here a minute. Let's all make sure we understand this. From a graphical perspective, if I was to graph this thing right here, what's happening? What's this 1/2 mean? What do we call it? What would it be on the graph? Horizontal asymptote. Let's don't all forget that. When we do an x approaches infinity kind of limit, what we're finding is a horizontal asymptote. So when you get one that doesn't have a number, like this one, then what is happening on this graph? No. As x approaches infinity, these outputs are doing what? It's going up like so, like an x squared or an x cubed, where it's just going up to infinity. It's just going up to infinity. Okay? Now, it turns out it's kind of a slanted asymptote. You know what, remember when we crossed out the 1 here and then we said x squared over x, which is just x? What's really going on here, what we did, by doing that, we just found the slanted asymptote. In other words, what this is telling us is as x goes to infinity, this graph is approaching x, which what it means is, instead of that one problem where we got 1/2, and that means it's approaching y equals 1/2, this means it's approaching y equals x. Here's the line y equals x. What this tells us is that this graph is approaching, now I'm not sure which way it's doing it, but it's probably a vertical asymptote is probably doing this. Oops. There's a vertical asymptote at 0, because it'd be undefined at 0. We'd get 1 over 0. So there's a vertical asymptote here. So if you were to graph this, it's doing this. So it's going to infinity, and it's got this slanted asymptote at y equals x. Just additional information. Not something you have to know for the test. But, okay, so that's what's going on there. And I'm guessing down here we have very much the same thing. If you were to graph this on your calculators, my guess is it looks something like that. Got a couple of branches in there. Okay? All right. So what were we saying on this one? 0. Because the top goes from -1 to 1, and you're dividing that by a big number. Okay? So it's going to alternate between negative and positive. It's getting smaller and smaller and smaller. It's approaching 0. Okay, what about this one? Can we cross out the 2?
No.
Brennan, tell us why we cannot cross out that 2.
Because cosine of negative infinity is either -1 or 1, and if you add either of those two, it'll still be positive.
When, Logan, can we cross out that 2? Say it again. Why did on that 1, when could we cross out this 2? When it's insignificant compared to the thing next to it, right? When you have 1,000,000,002, the 2 doesn't matter. But we don't have 1,000,000,000 here. We only have -1 to 1. So the 2 matters very much. How many people tried to cancel out that 2? Be honest. Yeah, and Brenda, that's why I called her Brenda, because she did the same thing. Okay? All right? So even though we have new, freer license to cancel out things, which we said was kind of cool yesterday, we still can overdo it, right? So think about it this way. Think about it this way. This is the bottom is the cosine shifted up 2. What happens when you take cosine shifted up 2? All positive values. So what you're going to get here is you're going to get positive value. The bottom here is going to alternate between 1 and 3. It's just going to alternate between 1 and 3. So it's going to be just positive numbers. What's the top doing? Really big. So really big, negative, but that doesn't matter in this case. So it's really big divided by some positive number. So it's going to get to be a really big, well, I shouldn't say it doesn't matter. It does matter in this case. So we're going to have a really big negative divided by just some positive number. That's going to keep getting really big negative. Was this the one you were asking about, Keaton? Is this 16?
Yeah, that's one of mine.
Negative infinity. So as x gets really big negative and you cube it, it'll stay negative. And the bottom will always be positive because of the +2. So the +2 is very key there. All right? Yes, Logan.
If it was x squared, would it be positive?
Yes. If that was x squared, it would have been positive infinity because we'd had a big positive divided by some positive.
What
Okay.
if there wasn't the +2?
That would be a problem, yeah. If there wasn't the +2, so you guys were looking at it and you were saying, hey, I got a negative and I'm dividing by sometimes a negative, sometimes a positive. So what would happen is this would be, wow, that's interesting. Did anybody try graphing that? Somebody try graphing x cubed over cosine. Because what would happen is you'd have the top getting really big negative, and then you'd be dividing by these small numbers, some negative, some positive, and as this gets close to 0, you would get vertical asymptote. So everywhere cosine is 0, see, that's the problem. Everywhere cosine is 0, you're going to have an asymptote. So you're going to have, at pi halves and 3 pi halves, and you're going to have all these vertical asymptotes. And so you're going to have this graph probably down below, up above, and it's just going to be going all over the place. So we would say that that would be the limit does not exist, probably. Try typing this limit. I'm curious, in your calculators, let's do that. Just for the heck of it. Because the calculator sometimes on these limit problems, has some difficulty also. It's where we do derivative. It's in that template next to the 9, I think it is. It's one of those in there somewhere. You guys probably done if I can get this pulled up. And there's an infinity. Is there an infinity right on the keyboard?
Yeah, it's above the book next to the little inventory.
Okay, over there next to the 9 somewhere, you can get the infinity symbol. This new update is supposed to load fast. So what'd you get? So if you typed it in just the way the problem was, did it say negative infinity? Anybody get that done?
Yeah.
And then what if you leave off the 2? It says undefined. Yeah, because so x approaches negative infinity. And I don't like, I wish they would fix that. They say undefined on limits when it really should be. So what do we have on top of this problem? Execute. And then down here, if we do cosine. So I'm guessing if you graph that, if you graph this function right here, not with the limit, but if you graph just that function, it's a bunch of asymptotes. And so as you go out, it's just bouncing back and forth. Actually, we say the limit diverges. If it converges, then it converges to a single number. And another way of talking about limits is it diverges. It's just bouncing all over the place. Okay? So it wouldn't even be acceptable to say infinity in this case. So that's why on it does not exist, you could talk about justifying it because, well, what is it doing that it doesn't converge to a number? All right. We'll leave that up. All right, next one. What do you have on this one? This is 17. Why? Yeah, this is just a rate one. And this is something that I've seen asked many, many times on the AP test and in our practice AP test. Understand that exponentials grow faster. These both are increasing. Both get big, but exponentials get way, way bigger, way faster. Even if x was 1 billion, 2 to the billionth is bigger than 1 billion squared. Okay? Way big. All right? Even if this power was 1 billion, even if this was x to the billionth, you might say, well, billion to the billionth has to be bigger than 2 to the billionth. Yeah, but as it gets bigger and bigger and bigger, this power would stay 1 billion. So 1 trillion to the billionth, well, 2 to the trillionth, eventually that is going to overpower, and the exponential will grow faster. So, a little bit of a side note here on this. So, here is e to the x, and it grows very rapidly. If you compare that to x cubed, which also grows rapidly, the 2 to the x grows, or the e to the x grows way, way faster. Okay, and we're going to get into that here in another problem in a second. So this is bigger than this, so it's infinity. And so then what about this one? Is this 18? Okay, because what changes when you go negative infinity? Yeah, this is still big, but when you do 2 to a negative number, it's getting smaller, going towards 0. So you got the top getting small, bottom getting big. That's definitely a recipe for that going to 0, getting smaller. Okay? All right. Now, is this 19 now? This one, I'm guessing, was a really hard one, other than the fact it was odd. What did they say in the back for this one? 0. Okay. Well, this is really the same reasoning that Logan just said or Spencer said on this other one, the 2 to the x, or Brenna said, or whoever's saying. The 2 to the x and x squared, which one goes bigger, which one grows faster? These are both increasing functions. Now, you might have looked at those and been a little leery of even knowing them, so let's talk about them real quick here. These are inverse functions. E to the x grows very rapidly, which means it gets towards vertical very quickly. Well, what's that mean for its inverse then? It's going to get horizontal very quickly. Now, it doesn't get all the way horizontal, but it means it's going to increase very slowly. Right? Does that make sense? Because they're inverses. So if you look at a power function like x cubed, it grows fairly rapidly, but not as rapidly. And so therefore its inverse, which is x to the 1/3, this is what fractional ones look like. Now we have x to the 2/3, but it's basically the same thing. It's going to get horizontal, but not quite as rapidly. So they work in inverse of one another. So when we just said that an e to the x would get bigger much faster, then it's the other way around on one like this. This power is going to get bigger faster than this one is. And so this one is going to go towards 0. Okay, so this bottom one is increased faster than natural law. Okay, so an exponential increases very, very rapidly. A log increases very slowly. Okay, because they're inverse. All right, so there was a problem. I'll just tell you this problem right now. There was a problem on the multiple choice on one of our semester reviews, so you may run into this and see if you remember. And it said something like, how many times do these two graphs intersect? I believe that was the problem. How many times do those two graphs intersect? And it might even have been on the calculator. No, I think it was no. And so if you graph y equals x squared, and you graph 2 to the x, of course this graph comes through here, crosses like so, and then it hits again here at what point would those intersect at? 2, 4, right? Put a 2 in there, put a 2 in there, you get 4. So they're going to intersect back here at, I'm not sure what that point is, but they're going to intersect somewhere back here. So 2 to the x is this exponential that goes up like this. And then, if you graph them in just kind of a normal window, it looks like this. So, you would say how many intersections? 2, right? Well, guess what? They're going to intersect how many more times? Well, they can't intersect more than one more time. They can't start going, they don't go like that, do they? I mean, I don't think x squared is going to curve like that, are they? But what did we just say about 2 to the x? It grows faster, so it's going to eventually get going way up, whereas this one's going to be, right, not going as fast. So eventually, when 2 to the x starts really getting vertical, but it's a ways off of your calculator screen, and nobody ever thinks to, change their calculator screen and that kind of stuff. Or it could be a no calculator also, where you just have to kind of plot some points and think about it, too. It turns out there's 3. There's another intersection point where they'll eventually do that. Now, actually, I think it's not that hard to find. It might have been 3 to the x and x squared or something. It might have been something different. It's actually 4, 16, I think, right? 2 to the 4th and 4 squared, both 16. Which might be off of your normal calculator screen anyway. But again, how would you know that? Well, because you know about the growth rates of 2 to the x compared to x squared. That's what they're getting at in a question like that. Okay, so I've just seen that kind of concept asked a lot of different ways. All right, so we got that. And here's the other one I added, and then we'll come back and hit 20 and 21. This is the other one I gave to you. Now, we've already done one a little bit like it. This is one where you would just want to plug in your 3, so you get 14 over 0. So you should say does not exist, And then you want to do x approaches 3 from the left, and you want to do x approaches 3 from the right. Again, anytime you get something over 0 that does not exist, and then you need to go farther. And the only way you can get something over 0 is if it's x approaches, infinity. Or it's not x approaches infinity. It's got to be an x approaches 3 or 2, 1. So we can do it both sides kind of thing. All right? And so you plug in a number a little less than 3, which would make the small negative on the bottom, a little more than 3, make a small positive on the bottom, and you have your answers there. So this would be negative infinity, positive infinity, and there's your justification for the does not exist. Okay, and again, show a little more there, but that kind of thing. All right, number 20. Now these were really just kind of plug-in situations. On number 20, you had, what do you have, sine of pi over x, and x was approaching infinity. So what happens right inside here? Gets close to 0. And what happens to sine as as its input gets close to 0? It's at 0, right? And then this last one was kind of a strange one. I wondered if it was a misprint, but maybe not. They just said x approaches 0, right? And just plug it in. Sine of 0, 0, sine of 0, 0. That one wasn't too terribly interesting. Well, I was wondering if it was maybe going to be an infinity or something. Then it'd just be does not exist. But so I don't know. Maybe not. Maybe they just wanted to throw that in. All right. Yes. Well, that would be, probably not infinity. Let me think. Sine of infinity. So what's a sine direct do? Well, it just goes negative 1 to 1. Right? So as x goes to infinity, this just bounces back and forth from negative 1 to 1. Sine as an input, negative 1 to 1, would be kind of the same situation. Same situation. So it doesn't really converge. I mean, it wouldn't converge at all. And so that would be it does not exist. And I suppose I don't anticipate asking that, but I'd say that's what you'd say. Inside here, that goes negative 1 to 1. So when you look at sine's inputs from negative 1 to 1, it would just be, alternating values and not approaching anything. So that would be it does not exist. Okay? All right. Let's get your notes out then. And we've got one new thing to talk about as it relates to these limits. What it really is, we really have enough information to do all these different types of limit problems. But what we're going to do today is bring in the derivative. None of what we've done is talk really about a derivative, and we were hinting yesterday about how the rates are involved here. How fast, right? How fast are these things getting big or small? And so we've already kind of thrown that out there. So what I'm going to do is give you this technique that is something you can use if you want to. And we'll go back and we'll use it on some of the ones that were on today's assignment. Okay? It's just another option. Sometimes it makes the problem easier. Sometimes it actually might make the problem harder. So you can use it if you want, kind of a thing. All right. It is called L'Hopital rule. Now, I capitalize the L all the time, but in the book, I noticed they didn't capitalize the L. I don't know, it's French, so maybe you're not supposed to capitalize the first one. And it's not hospital. There's not an S in there, except at the end. L'Hopital, I think is how it's pronounced. L'Hopital, I don't know. I can't speak French, but. All right, L'Hopital's rule. And here's basically what it says. And I'm going to really paraphrase this in a simpler way. But it essentially says if a limit problem is 0 over 0 or infinity over infinity, then, and then I'm going to write this out. Now this could be either x approaches a or x approaches infinity or negative infinity, any of those situations. And it's going to be a fraction kind of problem because that's the only way you can get a 0 over a 0 or an infinity over infinity. So it's going to have to be a fraction scenario. Then that limit is equal to, and it's really kind of nice how this works, is actually equal to the limit of f prime over g prime. In other words, L'Hopital's rule says that if you get 0 over 0 or infinity over infinity, one thing you can do is just do the derivative of the top, derivative of the bottom, and then try to do the limit again. In other words, substitute in again. And not only that, but if you do that and you get 0 over 0 or infinity over infinity again, do the derivative again. Do the second derivative. Do the derivative of the top, derivative of the bottom again. Now, then you eventually might get like 5 over 0, and if you do, then it does not exist, and then you got to check the left and the right. Or you might get a number for an answer. You know, I mean, so it's still one of those things could happen. But, and this kind of makes sense, right? Because what does f prime measure? Slope or rate of change of f. And that's the rate of change of g. And we said what determines this limit is how fast this is increasing or decreasing compared to how fast this is increasing or decreasing. And that's what f prime measures. So it kind of makes sense that you should be able to do that. Now, for those of you that still have to pass the gateway test, don't confuse this, right? Like when we're doing the quotient rule, we can't normally just do the derivative of the top, derivative of the bottom, right? That's what we're doing, the derivative of a fraction, but that's not what we're doing here. We're trying to solve this limit problem. So what this formula is telling us is do the derivative of the top, do the derivative of the bottom, and then do the limit from there. So let's go back. Now, again, I can't emphasize this enough. You can only use L'Hopital's rule if you've got those two scenarios. So you start by doing direct substitution, and only when you have that can you do L'Hopital's rule. Otherwise, you can't, because think what's happening. Here you got something getting small over something getting small. So what we need to know is how fast are they getting small. Here you got something getting big over something getting big. So what we need is to know how fast they're getting big. But in other situations, you cannot use this. Okay? So if we go back to today's homework, could we use L'Hopital's rule in this one? Well, turns out we could have and got the right answer, but for the wrong reason. Is this an infinity over infinity or 0 over 0? No, it's 3 over infinity, which is just 0. So L'Hopital's rule doesn't apply. Okay? How about this one? 5 over infinity? No. Okay, so we still think through them the same way. What about this one? Was this infinity over infinity? Sure was. What's the derivative of the top? Derivative of the bottom? Pretty nice. However, the way we did it was pretty easy too, right? I mean, we had to be careful of not canceling stuff when we shouldn't have and that kind of thing. But this wasn't bad either. So, you know, it depends how hard the derivative is to do. But there would have been a pretty nice one to do L'Hopital's rule. I once had a group of students go to UNO for something. They went on a visit, and then while they were there, they had to take a test or something like a math placement thing. It had some calculus on it. So I'm not sure what kind of group they were with or why they were there. This is a number of years ago. And they were doing limits. There were some limits on there, and they were talking with their group of other high school students who'd come from some other high schools around Nebraska that were in calculus. And they were talking about, what'd you get on that limit problem, blah, blah, blah. And my students said, well, we use L'Hopital's rule. L'Hopital's rule. None of them had studied L'Hopital's rule. It's not in the AP syllabus to do it. They do in college calculus. Sometimes they must do it later. Maybe, I don't know why. They save it for so much later, why they hadn't done it. So it's not, so on the AP test, there won't be any problems where you have to use L'Hopital's rule. But it's just kind of nice to know. It's so easy. I don't know why you wouldn't teach it, because it's such an easy thing to do. Anyway, so we felt pretty good about that. We knew L'Hopital's rule. Nobody else did. It sounds impressive too. That's the thing. You know, you tell them this is L'Hopital's rule, and even though it's not that big a deal.
Does it still work if that is like negative, positive infinity over negative infinity? Because when
Yes.
they case in this one?
Say that again. Yeah, this is actually a positive over negative. Good question. When we talk about the infinity over infinity situation where it applies, it doesn't matter if it's positive or negative positive. Yes, that does not matter. Okay. What about this one? This was infinity over infinity as well, right? So the derivative of the top is 2x, derivative of the bottom is 1. Now remember, once you do L'Hopital's rule, then you plug in to see what you get. So we get this, now we let x go to infinity. Oh, 2 times infinity is infinity. So, again, infinity. So we could have got it by doing that on that one. Okay, another one that's infinity over infinity. So we do the derivative, we get 2x. We do the derivative of the bottom is 4x. Now we can either cancel the x's or we could do it again. We could say, hey, that's still infinity over infinity. So we could do the derivative again, get 2/4 or 1/2. Okay? What about this one? No, this was -1 to 1 over infinity. So that was 0. So that is not a L'Hopital's rule. Same thing here. We got infinity over, kind of a 1 to 3 thing. So that is not L'Hopital's rule. This was. Okay, and this was one we really had to think about a little bit. Now, some of you knew that, hey, this is going to get bigger faster. But if we do the derivative of the top, that'd be 2 to the x ln 2. The bottom here would be 2x. That's still infinity over infinity. So we do the derivative again, which would be 2 to the x ln 2 and an ln 2 just tacked on. And then the bottom would be 2. And so now we see, okay, as x goes to infinity, this is still going to be there, still going to get big, divided by 2, so it's going to infinity. So there's a case where you have to do it twice. But again, if you know how fast these grow, I think L'Hopital's rule takes longer in that one. So I'm not sure it's a good way to do that one. Okay? Same thing with this one. Well, no, that's not true. This is 0 over infinity, so this is not a L'Hopital's rule. We would not want to do L'Hopital's rule then. Okay? Here we had infinity over infinity. Okay, this would be a good one to look at. Here we had infinity over infinity, and those were some tougher functions to think about. So let's do L'Hopital's rule. This would be 1 over x divided by what? 2/3. Got a little algebra to do here. It's not horrible though, right? This 2/3 would flip up there as a 3/2. You could move this up top. So on top you'd have an x to the -1 and you'd have an x to the 1/3. What's that? See how I did that there? This is x to the -1. This would flip up as x to 1/3. Add the powers. Right? Now, as x gets really big, what's going to happen to that? Small. Go towards 0. 0 times 3/2 is 0. So there, L'Hopital's rule would have worked pretty nicely. Now, you had a little more algebra to do, but if you didn't know what was going on with these functions, it's a no calculator, L'Hopital's rule would save you on that one. Okay? And then our last two, I don't think, were ones where we had to do that. Okay, so now let's talk about this. So last bit of notes here to do, and then we'll give you some work time. What time are we at? 45? Is that right?
Yeah.
45? Okay. All right, indeterminate form. So indeterminate means, hey, you need to keep going. There could possibly be an answer, a limit. Well, 0 over 0 is the one we've always had, which really means something small over something small. But which one's getting small faster, that's kind of the key. But there probably is an answer, very well could be an answer. Infinity over infinity, so those are the two where we can do L'Hopital's rule. But now we got this other one that we talked about yesterday. Right? These are the two that we can do L'Hopital's rule on. This third one is the 0 times infinity. Because what we have there is something small times something big. The question is, which one's getting small or big faster? Which one wins this tug of war that they've got going on there? So if the one getting small is getting small faster than the one getting big, then the whole thing's going to get small, go towards 0. Or if this one's getting big and so forth. It might go to infinity, or they might just, this one's getting big twice as much as this one's getting small. So maybe then the limit is 2. And maybe it comes out to be an actual number. All right? So you cannot use L'Hopital's rule on that, though. Because L'Hopital's rule only works infinity over infinity or 0 over 0. So we have to turn it into a fraction. Now, if you think about this a minute, though.
I thought that was actual experience. Showtime.
Sounds like Mr. Cool's Algebra 1A class, probably.
We have to do something to keep them.
Now, here's the secret to this. 0, or a really small number, is the same as that, essentially, right? I mean, 1 over a really big number, not just 1, but any constant, over a really big number, right, is basically 0, a really small number. And vice versa. A really big number is kind of like the reciprocal of, right? We can almost think, kind of like 2 and 1/2 are reciprocals, we can almost think of 0 and infinity as reciprocals, right? Something getting really small, the reciprocal of that is something getting really big, and so forth. We can use this in our favor for this right here. Okay? We can take 0 over infinity, and we could write it as, we could write the infinity as down here, something like this. Right? Think about what I just did there. If I, timesing by infinity would be like the same as dividing by its reciprocal, right? And dividing is the same as multiplying by the reciprocal, that idea. But now what's 1 over infinity? Essentially. 0. So now what I've done is turned that into 0 over 0. Does that make sense? I've turned that into a 0 over 0. Or I could do the reverse of that. I could leave the infinity up there, and I could divide by the reciprocal here. Right? Now both of these, but so what do you get? What's 1 over 0? Basically infinity. So what I've done is turned it into an infinity over infinity situation. Okay? So this idea of dividing by the reciprocal. It's like if you take 2 divided by 1/2. That's the same as multiplying by, what's dividing by 1/2? Same as multiplying by 2, right? So multiplying by infinity is the same as dividing by 1 over infinity. Or multiplying by 0 is the same as dividing by 1 over 0. Okay? So what kind of problem would that look like? Well, it might look like this. Limit as x goes to infinity of x squared times ln x. Okay? Now what you have is infinity, oh wait, that's not 0. What it, oh no, here's what I want. I'm sorry. This is not approaching infinity. This is approaching 0 from the right. Now I had to add that from the right. Why did I have to add the from the right in this problem? Why? And where is there no from the left? In the natural log function, right? Everybody, we had the natural log function up here earlier. Okay, the natural log function looks like this. You cannot put negatives into the natural log function, right? So there is no from the left on the natural log function, only from the right. So we had to add the from the right. That's not something you would have to know, but if they gave you this problem, you'd be like, why did they only do from the right? That's why. Okay? So now what do we have here? So so we can plug in our 0, at least for this part, and we have what? 0. What about natural log as x approaches 0 from the right? What's natural log doing? Here's the graph, negative infinity. So what I have is a 0 times infinity situation. Okay? So what I can do with this is I can rearrange this and make this ln x over 1 over x squared. Now, isn't this red thing the same as the original problem? Isn't that the same? Dividing by 1 over x squared is the same as timesing by x squared. But now what do I have? As I approach 0 from the right, this will be negative infinity. And approach 0 down here, I'll have 1 over a really big number. What's 1 over a really small number? Really big number, right? As x goes towards 0, I'm going to have 1 over a really small number, which is a really big number. I've got infinity over infinity now. So I've rearranged it so that I can now use L'Hopital's rule. Now, it's possible that I could have looked at this and said, hey, I got something getting small compared to something getting big. Which one's going to win the fight? is this getting big, big negative, faster than this one's getting small? Well, think about x squared at 0. Is it getting small very fast? It's kind of leveling off there, isn't it? This one's getting big really fast. It's going almost vertical, right? So which one's going to win the race? You would think it's going to be this one going to infinity, right? But let's see what happens. So you might be able to reason your way through that one without doing this, but here's how L'Hopital's rule works. So we do the derivative of the top, so let's do that in blue. So the derivative of the top is 1 over x. Derivative of the bottom, this would be x to the negative 2, right? So what's the derivative of that? Negative 2x to the negative 3. Now 1 over x is the same as x to the negative 1. So how could we do this? We could bring this negative power up, or we could just subtract them, I guess. That'd probably be easiest. Negative 1 minus negative 3. Positive 2, isn't it? So I have a 2 on the bottom. So I'd basically have a negative 1/2 x to the second. Right? That's how that would reduce. This negative 2 is on the bottom, so that's a negative 1/2. Or I could think of flipping this up here as an x cubed, add the powers, and you get x squared. So now, as x goes to 0, what do we get? Wait a minute. No, we get 0. No, that doesn't sound like what I was talking about before. I was saying going to infinity, wasn't it? Where'd I go wrong? As x approaches 0 from the right, that's getting big, that's getting small. Small 1. I gotta think about that one. Good thing for L'Hopital's rule. L'Hopital's rule says 0. Type it in your calculator. Let's see what we get. Well, I probably just underestimated how fast 0 is, how close, because it's flat, so it's right down near 0. You know what I mean? It's down near the x-axis because it flattens out there. So maybe it's just much, for any given value close to 0, it's just much closer to 0 than that is big. Yeah. And this is definitely more exacting if you do the right algebra than this idea of, well, this is getting bigger faster. I mean, with powers and exponentials, it kind of does, but that's.
Actually, I guess that's not how the graph's supposed to. Did we go off of the graph?
No, I was just going off the graph of ln x when I was doing this. I was just saying ln x, how as you approach 0 from the right, this is getting big, negative, it's fairly vertical. And then I was just thinking of the x squared graph. So yeah, I didn't graph this actual thing. What does it look like?
It's kind of like, it starts at 0 and then goes down just a little bit and then just goes up.
Yeah. But we're just checking that it's at 0. Yeah, so interesting. Well, yeah, once you get past 1, natural log's positive and so is x squared. So it's only negative in that little bit between 0 and 1. But yeah, interesting. All right, here's another one. Let's do one more and then I'll let you go. Limit, as x approaches infinity, x times e to the negative x. Try that one. Using kind of this same, well, first of all, let's just make sure. Is this a L'Hopital's rule? Well, not right off the bat, it's not, but what do we got? As x goes to infinity, this is going to infinity here. What about e to the negative x? Getting really small. So again, we have a 0 to infinity. So rearrange that and use L'Hopital's rule. All right, so if you thought of a good thing to do, it doesn't take very long. Here would be, on the left would be a good way to do that. Now, I kind of cheated a little bit there. I left the x on top, and then we said do the reciprocal, divide by the reciprocal. So a lot of you might have done 1 over e to the negative x, right? But what is 1 over e to the negative x? E to the x, right? So I can actually just take this negative power and flip it down to the bottom, and then I've got my L'Hopital's rule, because now it's infinity over infinity. Now again, isn't this one where we could say that we know the bottom's getting big way faster, right? I mean, this is really one where you can say the bottom is big way faster than the top, so this is going to 0, and you don't need to use L'Hopital's rule. Now, if you flip the other one, then this gets into a whole big mess, to be honest with you. This gets into 0 over 0, which you can't even, you do the derivative and it's still 0 over 0, do the derivative again, it's still 0 over 0, do the derivative again, it's going to be 0 over 0 forever. Okay, where you have, so that's a bad choice of a way to go. This is an easier way, but it is one that I think you could probably just reason your way through without really even doing L'Hopital's rule. Okay, so for your homework, you've got a number of these to do. The 4.2 day 2 homework, there's a few in the early stages where you're doing some graphing. Okay, and then, or you're not doing graphing, they have some graphs. Some of the functions are graphs, and so you have to, look at them that way. But you'll get a chance to visit with each other and work together here for a while. Now, on the last section, 56 through 80, it says M4, that means multiples of 4. It's kind of like the gateway, page 195. I think you got to do more, and that's up to you. I mean, so if you want to do odd ones through there so you can check your answer, of course you can always type in the calculator too, or just do the multiples of 4 if you feel comfortable, that's enough, but you could do any of those in 56 through 80, for practice. Okay, because there's going to be a number of them on the quiz that are going to be like those, these just limit problems like 56 or 80, so that's a pretty good practice set right there. Okay, now use L'Hopital's rule if you can. If you can't, obviously don't use it. And if you can use it, maybe it's easier to not use it, like this one we were talking about here. I mean, I don't care. I'm not going to make you use L'Hopital's rule. It's just one of the tools you have if you need it. All right. Rest of the time's work time.